Okay, this problem says let R be a ring with unity and let A and B be unit of left R modules. In addition, suppose F from A to B and G from B to A are R module homomorphisms such that the composition G composed with F is the identity map on A. Show that B is isomorphic to the image of F directs on the kernel of G as R modules. So to exhibit this isomorphism, we will define explicitly a R module isomorphism and check that it is an R module homomorphism and that it is a bijection. So let's define psi from B to the image of F directs on the kernel of G by uh, psi of B is equal to the ordered pair F of G of B, comma, B minus F of G of B. Okay, so first we should make sure this is indeed well defined and sending things where we want it to be. So this is well defined since G of B minus F of G B is equal to G of B minus G of F of G of B, uh, using the fact that G is a R module homomorphism and thus in particular a additive group homomorphism. And so now this is G of B minus function composition is associative, G composed with F of G of B. But remember that by hypothesis, G composed with F is the identity map on A. And so this just becomes G of B minus G of B, which is 0. So B minus F of G of B is in the kernel of G as we need it to be, and also clearly um, F of G of B is an element of the image of F. Okay, so this is a valid way to define our map, and now we need to check that it is a R module homomorphism and that it is bijective. So let's do that. First, we'll check that it's an R module homomorphism. So to do that, let's consider two elements B1 and B2 and look at psi of B in B and psi of B1 plus B2. Well, that will be F of G of B1 plus B2, comma B1 plus B2 minus F of G of B1 plus B2. Okay, and then again, we're just repeatedly using the fact that F and G are R module homomorphisms in the appropriate directions, F from A to B and G from B to A. So this is F of G of B1 plus G of B2, since G is a R module homomorphism, comma, B1 plus B2 minus F of G of B1 minus, or plus G of B2. And that is equal to F of G of B1 plus F of G of B2, this time using that F is an additive group homomorphism, comma B1 plus B2 minus f of g of B1 minus f of g of B2. And that is going to be, um, so uh, this is in the kernel of, or sorry, the image of f direct sum the kernel of g. And uh, as an R module in particular as an abelian group addition in that R module is component-wise, and so we can split this up as f of g of B1 comma B1 minus f of g of B1 plus the ordered pair f of g of B2 comma B2 minus f of g of B2. And now this is clearly has the form of psi of B1 plus psi, this here is psi of B2. Okay, so that's one thing we need to check. Of course, this is quantified for all B1 and B2 and B. Now, for all R in R and for all B in B, we need to check that R phi of B is equal to phi of RB. Well, what is this? This is R acting on f of G of B, comma B minus f of G of B, just by definition of psi. And then R's action on this R module that is the direct sum of the image of f, direct sum kernel of G. That will be, again, component-wise. So this is going to be R acting on f of G of B, comma, by the module axioms, this will be RB minus RF G B. And this will be, now we'll use the fact that F is a R module homomorphism. So R, F of something is F, R times that, F of R acting on that something. And same for G, we'll just do those in one shot here. So this is F of G of RB, comma RB minus f of G of RB. We've sort of done two steps at once here. And this is now clearly psi of RB. Okay, so psi is an R module homomorphism. Now let's check that it's a bijection. So let's do injective first. So suppose psi of B1 is equal to psi of B2, then, well, by definition of psi, this says that the ordered pair f of G of B1, comma B1 minus f of G of B1 is equal to this ordered pair f of G of B2, comma B2 minus f of G of B2. Okay, now ordered pairs can only be equal if each of their corresponding components are equal. So this means that f of G of B1 is equal to f of G of B2, and also that B1 minus f of g of B1 is equal to B2 minus f of g of B2. And okay, so these are equal, so these are equal, so these, uh, by additive cancellation, B1 has to be equal to B2, so thus B1 is equal to B2. So psi is indeed injective. All right, now let's check that it's surjective. Okay, so now let B1 comma B2 be an element of the image of f direct sum the kernel of G. Remember, f is from A to B, so something in the image of f is an element of B, and G is from B to A, so something in the kernel of G is also living in B. That's why we're labeling this B1, B2. So, okay, what does it mean for B1 to be in the image of f? Well, then, so there exists some A in A such that f of A is equal to B1. And what does it mean for B2 to be in the kernel of G? Well, it means that G of B2 is equal to 0. Okay, so now we need a candidate for what's going to map to B1, B2, and we claim it'll be B1 plus B2, or yeah, um, B1 plus B2. I'll write that as B2 plus B1. Okay, so this is indeed an element of B, because B1 and B2 are, and so their sum is. Um, um, and, well, what is this equal to? Well, psi of B2 plus B1 is the same as psi of B2 plus f of A, because B1 is f of A, and that is equal to f of G of B2 plus f of A, comma, B2 plus f of A minus f of G of B2 plus f of A. And the parentheses are a nightmare here, but I think that's the correct number. So that is now we're going to use again the fact that f and g are R-module homomorphisms, and we're again going to use the fact from the problem statement that G composed with F is the identity in a minute. So, all right, what's this? This is F of so G of B2 plus G of F of A. So G of B2, but G of F of A, remember G composed with F is the identity. So G of F of A is just A, so plus A, comma, B2 plus F of A minus F of what? Well, G of B2 plus G of F of A again, but G of F of A is just A since G composed with F is the identity, so plus A. Uh, okay, and this is, well, G of B2 is 0, and F is an R-module homomorphism, so it's going to send 0 to 0. Uh, so this is just, you know, f of 0 plus f of a, comma, b2 plus, um, oh, what's f of a? F of a is b1, so b1, minus f of G of B2, but G of B2 is 0, so this is F0, and then minus F of A. Okay, as we said, F of 0 is 0, so this all become the left coordinate is just F of A, and F of A is B1, so that's B1. And what do we have here? We have B2 plus B1 minus F0, 0, so that we can ignore that. And then F of A is B1. So we have plus B1, we have minus B1, this goes away, all this goes away, and we're just left with B2. So B2. Great, that's what we need. So psi is surjective. And this completes the proof that B and the image of F direct sum kernel of G are isomorphic as R modules.